Welcome back to Calculus 2, Section 4.2, Direction Fields and Numerical Methods. In this section, we have three topics to go over. We'll introduce the notion of a direction field, talk about equilibrium solutions, and then go over Euler's method, a numerical method. Let's get started. Here we're looking at a portion of the plane. At various points in the plane, we have identified line segments. Each line segment has a slope. So for each line segment, find the corresponding point. And then at that point, there's an x-coordinate, a y-coordinate. And as you move to various points, the x and y coordinates are changing, and so too does the slope of the line segment. In Chapter 4, we're going over differential equations. A first-order differential equation means that the highest derivative count is the first derivative. If we have a differential equation where we can isolate out the first derivative in terms of a function of the unknown function y and the independent variable x, then by picking points in the plane, we can identify an x and a y, and thus produce some value, which we can assign to be the slope of the tangent line, i.e. the instantaneous rate of change, and thus draw a short line segment with that slope. Okay, let's look at this definition. A direction field, otherwise known as a slope field, is a mathematical object used to graphically represent solutions to a first-order differential equation. At each point in a direction field, a line segment appears whose slope is equal to the slope of a solution to the differential equation passing through that point. So one purpose of a direction field is to graphically represent solutions. Nice. In particular, this direction field corresponds with the differential equation y prime set equal to independent x minus the unknown plus a constant 10. Let's pick a point. Let's pick the point 0, 9. So for x, if we plug in 0, and for y, we plug in 9, then y prime would be positive 1. Thus, if we want to move away from that point that we just picked, we should move away at a rate of change of 1. However, by moving at a rate of change of 1, we are changing x and changing y by an equal amount. And thus, y prime at the new location will remain 1. In other words, we get the red line. On the other hand, if we were to change the y-coordinate to some value less than 9, and keep the x-coordinate 0, then the y prime would be bigger than 1. In other words, moving away from this black dot, moving away from that black dot with an instantaneous rate of change bigger than 1, we would move towards the previous line of slope 1. And as we approach that line, we would want to stay on that line. All right, let's look at various other y's and corresponding integral curves. Nice. Now, instead of referring to that black dot as the black dot, we know that we can call that the initial condition, abbreviated IC. And then we're looking for an integral curve passing through that initial condition. And we can term that integral curve the solution curve. Nice. In other words, this curve solves the differential equation, which provides this direction field. Very good. So that is a direction field. Let's look at the idea of an equilibrium solution. Here we have a different direction field, and there appears to be two different horizontal lines that can be sketched into this direction field. This direction field has differential equation 10y prime set equal to the product of two binomials, unknown y minus 1 and unknown y minus 10. Recall that y prime is the instantaneous rate of change. So if you end up with the unknown y taking a value of 1, you'll have that the instantaneous rate of change is 0. In other words, independent of x, the rate of change will always be 0, which we know is a horizontal line. The same thing occurs if the output y takes the value 10. That independent of x, the rate of change will always be 0. Let's sketch in those lines. We have two green lines here. The green lines are given by the equations y equal 1 and y equal 10. And we term these lines equilibrium solutions. They're at equilibrium because there is no change in the solution. Solution remains what it is. Nice. Now let's formalize that in a definition. The differential equation y prime given by f of xy has an equilibrium solution in the form of y equals c, where c is a constant. Good. Let's come back to the direction field we were looking at, which has two equilibrium solutions, y equal 1 and y equal 10. And then let's draw in some sample solution curves. Let's suppose that we take an initial condition with initial output as a negative quantity, sketch in the solution curve, and we see that the solution curve for x's getting larger is going to tend towards the equilibrium solution. On the other hand, if we pick an initial condition between 1 and 10 strictly, then the solution curve will tend down towards y equal 1. So in the previous two cases, initial condition less than 1 for output, the solution curve tends up towards y equal 1, and an initial output at 0, being between 1 and 10, the solution curve tends down towards y equal 1. On the other hand, if we consider this solution curve and look backwards in time, we can see that if we took our initial output to be anything strictly less than 10, then the solution curve is going to move away from the equilibrium solution, y equal 10. Let's bump this initial condition up above y equal 10. So consider at time t equals 0, an initial output which is greater than 10. What do solutions do thereafter? They produce outputs that get bigger and bigger and bigger. In other words, outputs move further and further away from 10. Okay, so this is leading towards the notion of equilibrium solutions can possess different types of behavior in their ambient space, that the direction field y equal 1, if we start with an initial condition not equaling 1, but something quote-unquote near 1, then all solutions will tend towards that equilibrium solution. We term this type of equilibrium solution asymptotically stable. Compare the equilibrium solution y equal 10 that taking an initial condition anything other than 10, no matter how close to 10 but not equal 10, you take the initial condition, the solution curve will move away from the equilibrium solution. Hence, y equal 10 is an asymptotically unstable equilibrium solution. Good. Let's look at another direction field. In this direction field, there seems to be only one equilibrium solution. The equilibrium solution y equal 0. And then consider solution curves with an initial condition, initial output negative, produces a solution curve which is asymptotic with the equilibrium solution. An initial condition which has initial output positive will have a solution curve which moves away from the equilibrium solution. So in some instances, solution curves move towards, and in other instances, the solution curves move away. This notion is termed asymptotically semi-stable. It's neither 100% stable nor 100% unstable. It's semi-stable. Okay, so here are some nice assignments for you. To begin, first match each direction field with its corresponding differential equation. Then, match each differential equation with its general solution. And for each general solution, determine a particular solution corresponding with an initial condition, y of 0 equaling 0. Nice. Then come back to the direction fields and sketch in a solution for an initial condition 0, -1. Fantastic. And we also went over the notion of equilibrium solutions and their asymptotic stability. Identify any equilibrium solutions and classify its stability as stable, semi-stable, or unstable. Fantastic. So we've gone over direction fields, a graphical visualization of solution curves, which led towards the notion of an equilibrium solution, and looking at the ambient space of an equilibrium solution, we could then classify solutions as stable, semi-stable, or unstable asymptotically. Very good. So now the second part of this section is on numerical methods. We've had a section on numerical integration, which was taking a Riemann sum written out in various ways. Left endpoints, right endpoints, midpoints, trapezoid, or Simpson's rule. Now we'll do a similar notion of coming up with a numerical procedure to derive a solution to a differential equation. This method that we'll go over is called Euler's method. So we have a direction field. There is a black dot labeled IC, the initial condition. There is a second dot, a red dot, which we'll come to briefly. And IC is on the solution curve sketched in black. Remember that we can pick any point on the solution curve, and thanks to the direction field, have a notion of what the instantaneous rate of change is. Now, the red dot may appear to be on the solution curve, but in fact, the red dot is a point on the tangent line to the solution curve. And thus only for x-coordinates, which are nearby the x-coordinate of the initial condition, does the red dot appear to be close to the solution curve. Okay. Well, let's introduce notation lowercase h to be the difference in x values between the initial condition and the red dot. And we're going to term that h the step size. So now at this red dot, we can determine the instantaneous rate of change and use the instantaneous rate of change at the red dot to produce a second red dot. And so forth and so on. Here we have multiple red dots produced. And the method by which we produce these red dots, now to produce the red dot, you need an x coordinate and a y coordinate. The method which we use to produce the red dots is termed Euler's method. Let's make an observation. Stringing together the red dots produces a pretty good approximation to the solution, the exact solution. Now, there are differences, but in terms of the overall shape, it's quite good. If you're not happy with the variation, the difference in the outputs, you can take your step size to be even smaller and then produce red dots which better and better approximate the true solution curve. In numerical methods, you always have a balancing act between accuracy and cost. It's more expensive to produce greater accuracy. Taking a smaller step size will result in more computations. Okay, so how do we go about producing red dots? How do we produce a successive red dot given a current red dot? In other words, what is Euler's method? Given an x1 and a y1, how do I produce an x2 and a y2? How do I go from a red dot to a red dot? Okay. So Euler's method is a numerical method. When do you use Euler's method? You use Euler's method to numerically approximate a solution to an initial value problem. So this is an IVP. The IVP comes in the form of a first order differential equation where the y prime is isolated. To be an initial value problem, you need a differential equation coupled with an initial condition. Now, the initial condition is providing you with an initial x-coordinate and an initial y-coordinate. So this is the black dot in the picture that we were looking at previously. To go from this black dot and produce the first red dot, what we want to do is find x1 and y1. But if this is x0 and we use a step size h, then to go from x0 to x1, then on to x0 you add one copy of the step size. And then successive x coordinates are just adding in one more copy of the step size. So coming up with x coordinates is rather straightforward. You simply add in another copy of h. In other words, we start with our initial x coordinate and then add in however many runs we want to make. Recall that we can term slope as rise over run, and run is a change in x. Let's use that procedure then to start with our initial output value and produce successive output values, y1, y2, and so forth. So we want to start with our current. If we want to produce y1, we'd set it equal to the previous y value, y0, and then figure out how much to rise. Now the h represents a run quantity, and then the f is a y prime quantity. F being a y prime quantity, you can term that rise over run. So if this is rise over run and you're multiplying by run, then this product would be rise. Okay, let's do an example. And employ Euler's method in this direction field. This direction field corresponds with the initial value problem, differential equation. Y prime is 2 times input minus 2, and initial condition y of -1 being 1. So y of -1 being 1 tells us x naught is -1 and y naught is 1, i.e. the black dot. Our first objective is to produce the red dot given this step size h being 1/2. Well, if the original x-coordinate was -1, then the next x-coordinate, x1, is -1 plus the step size, or -0.5. Nice. What we're going to do is we're going to use the information at the previous location, the black dot, and determine what the slope, the instantaneous rate of change, is at that black dot. So we know that the initial y-coordinate is 1. We're going to take 1 and we're going to add run times slope to give us the amount that we have to rise. Our information on slope is provided by the previous dot, initial condition. That initial condition has y prime equaling 2x minus 2, with x given as -1. So y1 is the previous y quantity, plus run times slope, where slope is given by the differential equation. Plug in the previous x-coordinate, so 2 times x naught is 2 times -1, and then half of -4 is -2. -2 plus 1 is -1. All right, let's do one more. We have x naught, add in h, we get x1. We want to go to x2, 2x1, add in h, come up with x2 being 0. All right, now let's focus in on how to compute y2. Well, we use the same formula. y2 is the previous y value plus the step size, the run, times the slope. The slope where? The slope at the previous dot. So that's 2 times the previous x-coordinate, -0.5, minus 2. That's dictated by the differential equation. Plug in the values and get the next y-coordinate being -2.5. And this can continue ad infinitum, as many red dots as you like. This is Euler's method. Here's an assignment for you to employ Euler's method. You have a differential equation, an initial condition. Here is the direction field for that differential equation. The solution curve is sketched, as well as the solution, the approximate solution, given by Euler's method. Your job is to use step size, 0.2, and produce the coordinates of the first 2 red dots, x1, y1, and x2, y2. That brings us to the end of this section. Thank you so much for watching. Please like if this video is useful to you, and I will see you on the next one.